Okay, so 1 second, there was some problem, so let me check. Okay, so a little bit of problem, steam get disconnected, so we were already in the final step of solving the question. So we just integrated it and we apply the initial condition. So we can say at r is equal to r naught, we have our theta is equal to theta naught. Therefore, we get our theta naught will be equal to minus, and we have this is alpha upon r naught plus c. So from here we can say that our c is equal to theta naught plus alpha upon r naught. Therefore, we substitute for our constant c, we get this is our theta of r is equal to theta naught plus alpha upon r naught minus alpha upon r, and you can say that our theta naught plus alpha we can take as common, so this becomes 1 upon r naught minus 1 upon r, and we can substitute value of our alpha. So finally we get our theta of r is equal to theta naught plus 1 upon v and square root of k upon mu 1 upon r naught minus 1 upon r. So it means that a particle will be move with the radial velocity v if and only if the angular momentum, that is of L square rather, is equal to mu upon k. So we can just make a consolidated list of all the answers. So we can say our final answer. We get this as the particle can move with uniform radial velocity if we have our L square is equal to mu times k. And under this condition, we also proved that our V effective is our independent of r and is equal to value of is equal to 0. And our for angular motion, we can also prove that our theta first derivative is equal to 1 upon r square and square root k upon mu. And we also proved that our first derivative of radial distance r is equal to v, which is nothing but our constant. And the trajectory equation, which we just found out in the last, okay, is our, you can say the trajectory equation is our theta of r is equal to theta naught plus 1 upon v square root of k upon mu 1 upon r naught minus 1 upon r. We come to the next question, and this question states that for what value of n are the circular orbits stable when the potential energy of particle is given by u of r is equal to minus a upon r raised to power n, where a is greater than 0. So we have to find out the value of range of this value of n, so that we are having a stable circular orbits. Okay. And here also once again we are going to use the, you can say, for a effective potential for a central motion. And for that we considered a particle, so we can say for particle of mass m and angular momentum L, we can write that our effective energy that is dependent upon r is equal to our L square and 2m r square plus energy at a distance of r. And this u of r is given to us, so we can write this as our L square upon 2m r square minus a upon r raised to power n. And for our circular orbit, you can say a circular orbit at r is equal to r naught, the first derivative of the energy will be equal to 0. So we can say that our V effective prime will be equal to 0. Therefore, we can say that our d of dr L square upon 2m r square will be equal to minus, and we have this as L square upon mr cube. So this is the derivative of our first term. Similarly, we can find out a derivative of our second term, which is our a upon r raised to power n, which gives us a times n r raised to power minus n minus 1. And we substitute it, and its first derivative is equal to 0. So we can say that our minus of L square m r naught cube plus a n r naught minus n minus 1 is equal to 0. And from here we can write our L square upon m will be equal to n a, and we have this as r naught raised to power 3, and this will be coming as r naught raised to power plus 3 and minus 1 will be giving us 2 minus n. And for stability, the double derivative of our this V effective should be equal to greater than 0. So you can say for our stability, we know that our V effective, its double derivative, which is R naught, it should be greater than 0. So let's find out its second derivative. Similarly, we can do it separately. Double derivative of our L square upon 2m R square will be giving us 3L square, and it will be our mr raised to power 4. And similarly, for the second term, our double derivative of our r square will be equal to minus a r raised to power n, which will be giving us minus of right here. This will be equal to our minus a n. This will be our n plus 1 times r raised to power minus n minus 2. And therefore, we can combine them and we get this our u double prime effective, that is our r naught, will be equal to minus 3L square mr raised to power 4 minus an n plus 1 r raised to power minus n minus 2. And we substitute, we just calculated our L square upon m. So we get this will be equal to our 3 n a r naught minus n minus 2, and this is minus a n n plus 1 r naught and minus n minus 2. So we can just combine the terms, or we can take as a of n as common. This will be coming as 3, and we can also take r naught minus n minus 2. This will be giving us our 3 minus of n plus 1, and this will be coming as our n minus n plus 2. So it will be equal to a of n 2 minus n r naught minus n minus 2, and our a is greater than 0, and also our r naught is also greater than 0. Therefore, the sign of this u double derivative will be only dependent upon 2 raised to power n into this only term. Therefore, we can say that sign of u effective double derivative r naught, it depends upon our n 2 minus n, okay, and it should be greater than 0, that it should be positive. So therefore, for stability, we are having that n 2 minus n should be greater than 0, or from here we can write that our n should be less than 2 but greater than 0. So this is our range of values for which our n will be equal to the loops will be stable, okay. And if n is equal to 0, then that is a condition for our marginal or neutral stability, because double derivative of this u effective will be equal to 0 at this point. So we got the range of our n is equal to less than equal to, or we can say n should be rather less than 2 and greater than 0 for our stable. If n is greater than 2, this gives us instability. Next question. It states that a 2 kg mass rests on frictionless horizontal table and is attached to one end of massless spring. The other end of the spring is fixed to a frictionless pivot, and the spring exerts a restoring force of magnitude 3r newtons on the mass, where r in meters is the distance from the pivot to the mass. The mass moves in a circular orbit and has a total energy of 12 joules. Okay, so our total energy is given to us, and we are also going to find out what will be these 4 parts will be there. So we can just say that in order to find out the 3 questions rather. First is find the radius of circular orbit and the velocity of the mass. The mass is suddenly struck, giving it an instantaneous radial velocity of 1 meter per second directed outwards. Show that the state of the system before and after the impact on the sketch of the energy diagram. And part C, for the resulting motion, determine the maximum and minimum values of our R. So here also we are going to solve it for our energy basically. So we are given that we have a object, and suppose this is center of the object, and a spring is connected a body which is moving in a circular orbit, and its radius is given as our r. So here mass is given as 2 kg. Therefore we can say that the mass, which is mu, is equal to 2 kg, and we have spring force, that is F, which is given as 3 times r. Okay, so obviously it will be directly inwards toward the pivot point. So we are given spring force, which is a F, and that is equal to 3 times r, and it will be directly inward towards the pivot. Directed inward toward pivot. So the force F will be directed toward the pivot point. Let us suppose that pivot point is a P, and total initial energy E is given as 12 joules. Total energy, which is our initial, suppose that is our E, is given as 12 joules, and it is given that initially it is moving in a circular orbit. So let's find out our first part, that is radius and the velocity of the mass. And we are given that force is a central force. Force is central and towards pivot. Therefore we can write that force F is equal to minus of our 3r, and this is r unit vector. Therefore we can say that this radial force over Fr will be equal to minus of our 3r, and from here we can find out the potential energy. potential energy will be giving us F of R is equal to minus du upon dr, and which will be equal to minus of our 3r. Therefore, we can say that our du of dr will be equal to 3 times r. So, if we integrate it, we get our potential energy at a radial distance r will be equal to integration of 3r and d of r, which will be equal to our 3 by 2 r square plus c. Okay. And at a radial distance when r is equal to 0, so we can say for u of r is equal to 0, energy is equal to 0, so therefore value of c is equal to 1. C is equal to 0. So we get that energy at a radial distance of r is equal to 3 by 2 r square. And the effective potential, we can say that as it is moving, it will try to move in a circular, and there is force which is acting in the radial direction, the angular momentum is conserved. So we can say our angular momentum is conserved, or we can say our L is equal to mu r square theta single dot, and that is equal to our constant. Therefore, our total kinetic energy, or we can say kinetic energy our T will be equal to our half mass is given as mu and our velocity square, which comes as our r single derivative plus r square theta derivative whole square. And we can just open it, we can write this as our half mu r square plus L square upon 2 mu, and we have this as r square. Okay, here we have used this first derivative theta value in terms of L, substitute it, and we get the answer. Therefore, we get that the total energy that is our E will be equal to our half mu r square plus L square upon 2 mu r square plus u of r, and we can call this second part as our V effective potential at a distance of r. So we can say our V effective at a distance of r will be equal to L square upon 2 mu r square plus 3 by 2, because u of r we already calculated is our 3 by 2 r square. So this comes at 3 by 2 r square. And for circular orbit, we know that our first derivative radial distance will be equal to 0, as well as the second derivative of radial distance will be also equal to 0. Therefore, we can say that our derivative of our V effective with respect to our radial distance r will be equal to 0. And we can just derivate the V effective and equate to equal to 0. So this gives us our this will be our L square upon 2 mu r cube, and this will be coming as our 2 mu r cube, and this will be minus of 2, and this will be a plus 3 of r is equal to 0. this 2 and 2 cancels out. Therefore, we can write that our L will be equal to, this will be 3 mu r raised to power 4 and its square root. Therefore, we can say that our L will be equal to r square root of 3 times mu. This is our angular momentum for a circular path. Similarly, we can find out the energy for our circular orbit. Energy for circular orbit, and we just said that the radial distance first derivative will be equal to 0, and therefore we can say that our total energy E will be equal to our V effective times R, and therefore we get this will be equal to our L square upon 2 mu R square plus 3 by 2 and R square, and our L square is equal to our R square, R raised to power 4 and 3 mu. So we substitute it, we get this as our L square, we can write this as our 3 mu R4 and divided by 2 mu R square plus 3 by 2 and R square, and our mu and this square goes by 2, so this comes as our 3 by 2 R square as well as 3 by 2 R square. Therefore, our energy E will be equal to 3 by 2 R square plus second term is also 3 by 2 R square, giving us 3 R square, but the total energy is given to us as 12 joules. Therefore, from here we can say that our R is equal to 2 meters. So this is our first one. Now we can also find out the velocity, because we found out the radial distance, that is R, and we know that our tangential velocity that is our V will be equal to R times theta single derivative, and we just found out that is our the angular momentum R L is equal to mu R times V. So from here we can say our V is equal to L upon mu times R, and we also know that our L is equal to R square and square root of 3 times mu, and we substitute it because we know our mu as well as R, so this comes as 3 times 2 and multiply by our 4, which comes as 4 square root of 6. Therefore, velocity V will be equal to, we have our this L is our 4 root 6, and we have our mu is our 2 and distance is our 2. So this comes as our square root of 6, or approximately 2.45 meter per second. So we got our velocity as well as our radial distance, our R. Now we come to our energy and before and after the blow. So we can say our energy before and after, whichever part B. So let's find out our initial state and then we come to the final state. So we can say our initial state, which is our circular orbit, and for that we know that our radius is already we have 2 meters, and we have this first derivative will be equal to 0, and this energy is also given as our 12 joules. therefore we can write that our effective potential at a distance r, which is our L square 2 mu r square plus 3 by 2 r square, and L square we also know is our L square is equal to through mu r raised to power 4, and we substitute it, we get this as 3 times 2 and 2 raised to power 4. Therefore, we get that our L square is equal to our 96, and V effective, potential effective at distance r, so we get the V effective at a distance of r will be equal to 96, and this is 2 times 2 and our r square plus 3 by 2 and r square, and if we substitute the value of r is equal to over 2, therefore at r is equal to 2 we get our V potential effective at r is equal to 2 will be equal to, this comes as our 96 upon 416, so this will be coming as our 96 upon 16 plus 3 by 2 times 4, which will be coming as our 12. So this is our initial state, the effective potential at a distance of r. Now we come to our after the blow, so we can say that in the blow we are given that our instantaneous, that is a velocity, that is our single derivative, is given as plus 1 meter per second, which is our outward. And here our r, that is our unchanged, so that will be still will be equal to our 2 meters, and our this angular momentum is still will be conserved because the radial velocity is only in the outward direction. Okay, so there is no torque in it, so we can say our this angular momentum is conserved, and only the kinetic energy is going to increase by the radial part. So we can say the kinetic energy increases by the radial part. Therefore, we can write that our new kinetic energy, or we can say new energy rather, new energy is our E prime will be equal to over half m, m is represented as mu, and this is our r prime square plus V effective potential at effective r, and we can just substitute the value, and V effective we just calculated is our 12, and therefore we get this our new energy will be equal to half mass is our 2, and our radial velocity is given as our 1, so this comes as 1 raised to power square plus 12, so 2 and 2 cancels out, so this comes as our 13 joules. So this is our new energy. Okay, so it means the final energy after the blow will be 13 joule and before is our 12 joules. Now we have to find out the minimum and maximum value before and after the blow, which is our part C. Part C, the minimum and maximum are after the blow. Okay. So we know that our new energy is our 13 or we can also say that this will be our V potential effective at a distance of r, and we substitute it, we get this as 24 upon r square plus 3 by 2 r square will be equal to 13. So from here we can find out a value of our r, and for the sake of convenience let us assume that our r square is equal to x, because it will be quadratic in x. So we get this as our 24 upon x plus 3 by 2 more x is equal to 13, and so this gives us 3x square minus 26x plus 48 is equal to 0. And from here we are going to get two values of x. First one is, let us suppose, our x1, which is our 6, and second one is our x2, which is our 8 by 3. And for our x1 we can say that because x was equal to r square, therefore we can say that our r1 will be equal to square root of 6, and similarly we can say that our r2 will be equal to, and this will be equal to square root of 8 upon 3. And from here we can find out minimum and maximum value. Okay. So we can say that our r minimum will be equal to square root of 8 by 3, and we have our r maximum is equal to square root of 6. So these are the value of minimum and maximum after we provide a instantaneous radial velocity. And finally, in part B, we are supposed to plot the graph also, and for that we can just plot it approximately. So this is our radial distance, and we have our energy, and before and after the initial and final energy we already know. So we were given that initial energy was our 12, and final energy which we calculated is our 13 joule. And we got our minimum and maximum value of radius also, and we know that value of our energy is constituting of two components. One is our half kr square, and other one will be equal to our L square divided by 2m upon r square. So based on this we can write that our two components, one component is our, this component is our half k r square, and we have our also other component, that component is our L square upon 2m r square. Okay. And we can find out that our asymptotically or approximate, the graph is going to follow this particular shape, final energy. Okay, so this is our V effective. Okay. And we have two values of R, minimum and maximum. So minimum value, and this is our maximum value. So we get our R minimum, and we have our R maximum. Okay, so this is basically the energy of our this. So this completes all the questions. Thank you.